This part of the lecture will be focused on the extrinsic semiconductors. This lecture will be in continuation with the previous lectures of the semiconductor under equilibrium. I reiterate that the equilibrium is a condition where no external forces are applied. So far we studied the intrinsic semiconductors, but we studied them from the mathematical analysis point of view. So we mathematically analyzed the position of Fermi level EF. We derived the thermal equilibrium electron concentration, thermal equilibrium hole concentration, and the intrinsic concentration Ni for an intrinsic semiconductor. Now, which is known as an extrinsic semiconductor? We have till now studied that an extrinsic semiconductor is simply an intrinsic semiconductor which is doped with the impurities. Alright, so it is a pure semiconductor when doped with the impurities, gives us an extrinsic semiconductor. The pure silicon which we obtain is actually 99.9999999, that is 7 times 9% pure. This is the industrial grade silicon. So we can, looking at this figure, we can imagine that the purity is of a very high level. So then if we have a pure silicon, why do we dope? Why do we dope, or why the doping is done? It is done to improve the conductivity. Conductivity of the pure semiconductor. This doping, which is obviously the process of adding the impurities, doping is done in the ratio of 1 atom of dopant in 10 to the power of 6 atoms of the pure semiconductor. So the ratio is the ratio of the dopants to that of the pure silicon atoms is quite small, and this is done deliberately so that only the conductivity is affected, whereas the material properties remain the same. Okay, I'll not elaborate much on the process of doping because we have done this in our previous semesters. However, if you want me to have an additional lecture on it, I may just entertain your request. So we have pure silica or pure silicon, which is a group 4th element. When it is doped with the elements from group 3rd of the periodic table, we get an extrinsic silicon which is a p-type extrinsic silicon. Why is it known as p-type? Because of the abundance of holes. So we have holes which are greater than electrons n. That is what makes it a p-type. Similarly, when we dope the pure silicon is doped with the elements from group 5, we get an N-type extrinsic silicon. Why? Because here the number of electrons is greater than the number of holes. Okay, all right. Now, what should be the impact of doping on the mathematical, or let me just put it in this way, that we will analyze the mathematical analysis. We'll analyze mathematically. Let's just go for the mathematical analysis of doping on a semiconductor. Alright, now here the mathematical analysis includes again the distribution function, it includes the Fermi levels, and it includes the electron and the hole concentration. So all this we are going to do mathematically. Now let us first make a simplistic approach, that what will be the effect of donors, which are the dopants, donors, and acceptors on the energy band diagram. All right. As we said that the doping is done in the ratio of 1 atom of impurity in 10 to the power of 6 atoms of silicon, so that these impurities or these impure atoms are non-interacting. Fine, so that they are non-interacting. Non-interacting means that each impurity atom has its own contribution. So that levels are introduced by each atom, or we can just write it as each impurity, whether it's a donor or it is an acceptor atom. If these impurity atoms would have been interacting, then a band would have been formed. So there is no band formation of impurity atoms. So the impurity atoms do not lead to the band formation because they are spaced quite far from one another. So these impurity atoms which are introduced into a pure semiconductor, impurity atoms, they can be ionized. They become ionized when they lose the electrons or gain electrons. Alright, that is, ionized means that they carry a charge, or they can become non-ionized. That is, they do not carry a charge. Now, let us suppose that we have n number of impurity atoms, n. Among these n, some may be ionized, whether it's a donor or it is an acceptor. So we can say maybe this n is ionized, and there is, or let's use the same symbol. Yeah, among this, n may be ionized or n may be non-ionized. Here I am taking the case of a donor so that it carries a positive charge after losing an electron, and non-ionized with a charge of 0. And this ionized impurity and the non-ionized impurity will give us the total impurity. This is the total impurity atoms. So here these are ionized ones and these are non-ionized. Alright, so they add up. And another important thing is that after the addition of these impurities, the position of the Fermi level is also going to change. That is, the position of Fermi level changes after addition of the impurity atoms. Now see, as we know from the definition of the Fermi level, Fermi energy EF is defined as either the highest occupied, energy level, or an energy level where the probability of finding electron is 1/2. This holds for T equals to 0 Kelvin, and this is for T greater than 0 Kelvin. Now, if we extend this to the extrinsic semiconductors, the band diagram is going to change. So here are the energy band diagrams of an n-type and a p-type extrinsic semiconductor. In an n-type extrinsic semiconductor, we are drawing the band diagram similar to that of an intrinsic semiconductor, with the top of the valence band, the bottom of the conduction band, the intrinsic Fermi level EFI at the middle of the band gap. But here, in addition to EFI, we are drawing another energy level, which is the Fermi energy, that is EF for this extrinsic semiconductor, shown by the dashed line. Now, as shown in the figure, and the Fermi level is above the intrinsic Fermi level. And similarly, for a p-type semiconductor, the intrinsic Fermi level is again in the middle, whereas the Fermi level, which is a small which is written here, maybe it's not visible to everybody, EF. So here it's the Fermi level of this system. Fermi level of this system lies below EFI. Now, why does it happen? We can have two explanations. One from a theoretical perspective and another from an analytical perspective. Now see, here I'll write that for a p-type, EF lies below EFI. I hope at this point you're very well versed with what EFI is. So still I'll write down EFI is the intrinsic, it's the intrinsic Fermi level. Alright, now in an n-type, why does E of F lie above EFI and why does EF lie below EFI in a p-type semiconductor? Now, as we know that the Fermi level only gives us a picture of the electrons. Alright, so we know that the valence band is full of electrons, whereas in the conduction band there are very few electrons at the room temperature and the maximum are in the valence band. But in an n-type semiconductor we have majority carriers, which are the electrons. So there are the electrons which are contributed by the impurity atoms. So there are, so in an n-type material, in an n-type material, majority carriers are electrons. All right, and besides intrinsic carrier concentration, that is the thermal equilibrium carrier concentration, where our number of electrons is equivalent to the number of holes is equal to Ni, that is the intrinsic carrier concentration. We have the electrons which are being contributed by the impurity atoms. All right. So we have electrons which are being contributed by the impurity atoms, and this impurity level is somewhere near to the, so this impurity level, I'll write E impurity, because this impurity level is the energy which is contributed by the individual impurity atoms. So E impurity lies somewhere in the band gap, that is Eg. So obviously if we define Fermi level as an energy level where the probability of finding the electrons is highest, or the probability of finding the electrons is 1/2, so obviously we know that the impurity level contributes the electrons, so the Fermi level in an n-type semiconductor must lie somewhere near to the impurity level, obviously. And this impurity level has a very small distance. When it is the donor level, E donor has small energy difference with the conduction band. Alright, because we know that a very small amount of energy is required. It's almost of the order of 0.01 electron volts to release the electron from an impurity atom. Alright, so EF in an n-type, I'll now write EFN, that is I'm adding the subscript, I'm adding the alphabet n to the subscript to denote that the Fermi level is of the n-type semiconductor. EFN lies near to the conduction band. Why? Because the donor impurity level lies closer to the conduction band. So here we are not drawing a clear picture whether it lies above the donor energy level or below the donor energy level, but here we just conclude that it lies near to the conduction band. That means it is above the intrinsic Fermi level. Alright, and now similar explanation. This is from a theoretical perspective, and similar argument is for the p-type, because obviously the impurities are acceptors. So we have another energy level which is E acceptor, which is devoid of electrons. Acceptors accept the electrons, so the majority of electrons are near to the valence band. So E acceptor is also near the valence band, and therefore the intrinsic the Fermi level of the extrinsic semiconductor, which is a p-type semiconductor, now we'll write it as EFP, will lie close to the valence band, obviously. So now in this very case, E of FP will therefore be below EFI, that is the intrinsic. So this is the theoretical perspective. Now let us come to the now again we'll try to analyze the same situation using the mathematical analysis. Now let's say for an n-type semiconductor, we know that the intrinsic carrier concentration Ni is given by Nc exponent minus Ec minus EFI upon kT. Alright, this is actually the thermal equilibrium electron concentration, or the thermal equilibrium hole concentration. This is for an intrinsic semiconductor. And for an n-type semiconductor, the concentration of the electrons would be given by Nc exponent minus Ec minus E of Fn, that is the Fermi level, by kT. Alright, now let's just divide the two equations. It would be N upon Ni would give us exponent, when we divide and cancel out some of the terms, it would give us EFN minus EFI upon kT. Then we apply ln on both the sides, we'll get ln N upon Ni equals to EFN minus EFI upon kT. So we get EFN minus EFI equals to kT ln N upon Ni. So EFN would be equal to EFI plus kT ln of N upon Ni. Alright. So now we know for an n-type semiconductor, the number of electrons would be almost equal to the density of the donor atoms, or the concentration of the donor atoms, provided all the donor atoms are ionized. And Nd is much greater than Ni. Therefore, it implies EFN is greater than EFI, which means that the Fermi level EFN lies above EFI. And similarly, we can proceed for a p-type semiconductor and we'll see that EFP, that is the Fermi level in a p-type semiconductor, would be equal to EFI minus KT ln of P upon Ni. Alright. Now again, for a p-type semiconductor, the number of holes, the density of the holes is equal to the density of the acceptor atoms, provided all are ionized, and Na is much greater than Ni. Therefore, E of Fp will be equal to EFI minus some number. It will be some number, say x. So this means EFP will lie below EFI, that is the intrinsic Fermi level. Alright, so this is how we prove mathematically that the Fermi level in an extrinsic semiconductor does not lie in the band gap, but it lies somewhere near the conduction band for an n-type semiconductor because the density of the electrons changes. And for a p-type semiconductor, it lies near the valence band because the density of the holes is increasing. Okay, now we'll come to the distribution function. Distribution function in case of the extrinsic semiconductors. Now we know that the distribution function f of e, that is the Fermi function, is given by 1 plus exponent, it's e minus ef upon kt. Alright. Yeah. Now we'll use this distribution function to see the distribution of electrons because of the impurity atoms. Now, before this, we'll recall that we have earlier said that an impurity atom can be ionized, that means it carries a charge, or it can be non-ionized or unionized in case it does not lose an electron or it does not gain an electron. Okay, now we know that the impurity atoms in case of semiconductors belong to group 3rd or group 5th of the periodic table. Now let us here take the case of arsenic. Arsenic belongs to group 5th of the periodic table. Now this arsenic, given by the symbol As, it can be ionized or unionized. Arsenic becomes ionized when arsenic loses an electron. So it loses an electron like this. And we can reverse the same thing as when ionized arsenic gains an electron, it becomes arsenic neutral, that is unionized. So this one is a neutral, or we say unionized. Sorry, we can say that this is unionized and this one is the ionized. Okay, now if the concentration of arsenic atoms is Nd, because we know it's the donor impurity, so Nd can be ionized as Nd plus after losing an electron, or it may become neutral after gaining an electron. Okay, now in case of this impurity, which is a donor impurity, only one electron can be lost or gained. Okay, so therefore if this function, that is sorry, okay, let me use another color for this. Okay, so now if this function which is our Fermi function, is extended to the impurity atoms, it needs to be modified. Now, how will it need to be modified? Because here the case is of the one electron only. It means Pauli's exclusion principle is not followed, because Pauli's exclusion principle says that 2 electrons per energy level can be accommodated, and which is the principle governing the Fermi function as well. Whereas here the limitation of the impurity atoms is that only 1 electron can be lost or gained to become ionized or to become non-ionized. So we simply need to add a factor 1/2, that is 1/2. That is no 2 electrons, it can only have 1 electron, therefore 1/2 would be introduced into the above function. So it would be F now ED. Why? Because the impurity atoms introduce a level which is the donor level, discrete energy level, which is the donor. Yeah. So we can write F of ED as 1/1 plus 1/2 exponent ED minus EF upon KT. This is how the expression changes. Now we keep on wondering, because this expression is normally not given in the book of the lower semesters. So for this you can refer to the Physics of Semiconductor Devices by J.P. Collinge. It is the Physics of Semiconductor Devices. It's a book by J.P. Collinge. Okay, so here now this 1/2 factor is because only 1 electron is lost or gained, or one impurity atom can gain 1 electron or it can lose 1 electron. So that is why this half 1/2 is introduced there. Now this F of ED, the distribution function, is also equivalent to the ratio of ND unionized to the ratio of ND ionized, which implies ND neutral would be equivalent to the Fermi function of ED into ND positive. That is, how many are ionized together with the distribution function would give us how many are unionized. Alright, now from here we can do a bit of manipulation, as ND ionized would be equivalent to ND total, I'll write T, minus ND neutral or unionized. So we can write ND total minus, what is ND not equal to? It's equivalent to F of ED. Okay, so this is actually not plus, this is total. Yeah, that is, it would give us, which is appropriate as well, because it would give us this is the probability of the finding the electrons at the energy level ED, which would be a function of the unionized donor atoms to the total population of the donor atoms. This is how the distribution is going to change. So NDT minus, we can, instead of ND naught, we can write F of ED into NDT, that is total. Take it as common, NDT 1 minus F of ED. Alright, then what would we have? We would have ND plus would be equal to, when we do all the mathematical analysis after substituting the value of F of ED, we would get ND positive will be equal to ND total, NDT divided by 1 plus two exponent of minus ED minus EF upon KT. Alright, so this gives us the ionized concentration, the concentration of the ionized donor atoms in terms of the total concentration of the donor atoms. And similarly, we can have another expression as ND neutral as ND total upon 1 plus 1 upon 2 exponent ED minus EF upon KT. This is another one. And similarly, we can have for the holes as F of EA 1 upon 1 plus 1 by 2 exponent EA minus EF but negative upon KT, which is also equal to the density of acceptor atoms neutral upon the density of total density of the acceptor atoms. Alright, and simply we can just see the concentration of electrons at the energy level ED. Let's suppose it's N subscript D. It would be the total concentration of the donor atoms which is there minus the concentration of the donor atoms which are ionized, because the ionized ones are those which have lost their electron, whereas if we subtract the ionized ones from the total, it would be unionized, because unionized ones will be the only impurity atoms which would be holding the electrons. And similarly, the concentration of holes P at the acceptor level would be Na, that is acceptor concentration total minus the acceptor concentration which are ionized, that means which have already gained the electron. Alright. So we can do the calculations other way around as well. We can have the ionized acceptor atoms as the total, let me use the same notation, Na, capital Na negative, it would be Na total minus Na unionized, that is neutral. Alright, so it would be again Na total minus F of EA into N of AT. Taking it as common, it would be Na total into 1 minus F of EA. Do the mathematical manipulation and we would get Na total upon 1 plus 2 exponent EA minus EF upon KT. Now here we have the another energy levels, which are EA and which are ED, because here we have just seen this is Nd plus, that is ionized. It has some relation with Ed minus EF, and similarly the ionized acceptors have a relation with Ea minus EF. Now in the next part we'll try to analyze how this Ea and Ed will change the energy band diagram. So if you have any queries related to this lecture, you may write back to me at